lattice between them. That's welcome.
Yes. Also, I thank Professor Zhou Liujun to invite me to be here at a very well-nice city and country, and also it's my first time to be here. I'm very excited. Very nice place. And today I want to talk about this my recent work about this Fracton topology orders with boundary Toeplitz braiding. It's kind of a marriage between strongly correlated topological fields and weakly correlated topological physics. I will explain this bunch of terminology later. And in fact, actually, you can forget about all this terminology. Just remember that we are dealing with strongly correlated topological phase method, and the mathematical tool comes from the free Fermion topological instrument. This is our key message. Okay, I'm Peng from School of Physics, Sun-Yat University in Guangzhou, China. Okay. Yeah. Yeah. Okay. This is my collaborators, and Li Boxi is my PhD students currently in the fourth grade, and the boundary of the fourth grade. And the second collaborator is Dr. Zhou Yao. He was my former postdoc in Sun-Yat University. He is currently a postdoc in University of Hong Kong. The signal. Okay, let me start with the story about the topological order from this.
I forgot to share the screen.
Should I restart?
Uh,
Are you okay?
I don't think that's necessary.
Where should I start?
Maybe you can just continue.
Okay. Okay. Let me start with the story of topological order from this story of fractional corner Hall effect in 1980s, when I was born, 1980s. So the fractional corner Hall effect is very famous, strongly correlated physical phenomenon, which was won the Nobel Prize. And here's the very important progress of this fractional corner Hall effect is that the topologically proposed this very famous locking wave function for this very complicated shapes method. This is a very non-trivial approach to this fundamental physics, because conventionally we want to use standard perturbation theory to this Hamiltonian instead of wave function. And here people for the first time propose this tri-wave function to try to understand this method, rather than solving this complicated Hamiltonian. Okay, the very peculiar feature of this wave function is that the power of this polynomial is 3. This number 3 comes from this the factor that this fitting fraction is 1/3. Okay, fitting fraction 1/3 for this lowest lambda limit. Okay, in addition to this wave function, people also use alternative approach to study the fraction corner Hall effect, or we can call it as topological order in 2D. The approach is so-called hydrodynamic field theory, or we can call it as some kind of 2+1D T topological quantum field theory. In 2+1D, we use this Chern-Simons theory, which is kind of a T in 2+1D space-time to describe this the ground state of this fractional Hall liquid. And here we can find that this the Chern-Simons theory is written in this form. The coefficient 3 is quantized to integer, and this quantization of this prefactor is guaranteed by this large transformation. We don't need any symmetry to protect this quantization of 3. That's very important. So in that sense, we don't need any symmetry to protect the topology order in 2 plus 1D, the topology order. Okay, so here from this TKP, we can compute this very famous topological environment, so-called ground state dynamicity (GSD), which is only dependent on this genus of this manifold, where we put this Chern-Simons theory on. And this, for example, for the first torus, the G is 3, not like 1, so the GSD is 3 for this Chern-Simons theory. And in addition to this GSD, we can also have this can compute this number of superselection sector, or likely we can call it how many distinct topological excitation in this plus 1D theory. And also based on this three distinct distinct angles, we can compute the fractional charge carried by each angle. And then we can compute this data, so-called braiding statistic, braiding phase. We can move one particle around another, and we then the wave function will pick up AP phase. This AP phase can also compute from this Chern-Simons theory in principle, and also we can design this so-called fusion process to study this relation between different angles. Okay, so in addition to this data, if we put this theory on the open manifold with the boundary, we can deduce this boundary chiral theory, which can be deduced based on this so-called light tone gauge and open boundary condition. This is very standard result constructed many years ago. Okay, yes, it's not. I cannot change it. Oh. Okay. 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 In addition to the single component Chern-Simons theory, we can also have so-called multi-component Chern-Simons theory. We believe that this multi-component abelian Chern-Simons theory can describe all abelian topology order in 2 plus 1D. This is the formula of this multi-component Chern-Simons theory. Also, in the literature, we alternatively call it as K-matrix Chern-Simons theory, because its coefficient single number 3 now is changed to this symmetric integer K-matrix Kij. Kij is symmetric and an integer value, which is quantized by this condition of a large gauge transformation. And the second term is a particle term. Here, the integer vector L label the particle, and it's Q label this charge carried by each layer of this topological current. So this capital A is external EM3 to prove this charge characterization. And based on this theory, we can also compute the GSD for this kind of topology order on this any manifold. And also we can compute this mutual statistic between different angles labeled by L and L prime, respectively. And this theta characterizes this mutual statistic between L and L prime. This is very important data I will use later on, and here I use this square to highlight the result. Another topology data is so-called self-statistic, also we call it topology spin. We can use this formula to compute this topology spin. And in addition to this data, we can also compute the fractional charge. Use this formula. The take-home message is that in principle we can use this Kij, L, and Q, this function of data, to compute almost all interesting topological data for all abelian topology order in 2 plus 1D. And also there's a central charge, central charge, which is defined as the difference between this the number of positive eigenvalues of K and the number of negative eigenvalues of K. Okay, this is very standard result. Okay, and here is some example. So, for example, the simplest one is K equals 3, which describes this parallel state with fitting fraction 1/3, and also this is nothing but stacking of two layer Lofting states, and this K describes this the low energy physics of this very famous Toeplitz model. Also, we can call it Z2 topology order, and these two K are equivalent to each other because we can use this general linear transformation to transform one K matrix to another. These two K both describe the so-called twisted Z2 topology order. Also, we can call it double semi topology order. This
multi-component CS theory described fermionic.
Yes. As long as you have at least one entry along the cycle is odd. For example, this Lofting state is nothing but very simple fermionic theory.
Your previous page mentioned that that C central charge. I think you mentioned the C equals the positive eigenvalue minus negative.
Yes.
That means C must be an integer.
Yeah, you're right. So here is abelian topology order. Non-abelian topology order, the Chern-Simons charge is always integer. So for non-abelian, you can have chance to have the fractional.
That even for fermions, the central charge is still integers.
As long as this series is abelian. For fermion theory, you can also have abelian or non-abelian. For abelian theory, no matter if it's bosonic or fermionic, the Chern-Simons central charge is always integer. Yeah. So let me try to change page manually. Okay. So now the question is, can we apply this Chern-Simons theory, not computer science, Chern-Simons theory to 3D? 3+1 is real space. 3D. Chern-Simons theories interchangeably use 3D and 4D. You just be careful. So here, can we apply the Chern-Simons theory to 3D topological spaces? Because we are new generation of topological order fan. We have to survive to do something beyond 2D. So we have to do some higher dimensional, maybe 3D or 4D, 5D. Right? So here we want to ask this question: can we apply the Chern-Simons to 3D? Of course, we cannot, because this space-time integration is 2+1D. So we cannot direct use this theory to describe 3D theory, 3+1D theory. Because intrinsic 3+1D TQT is the so-called BF theory. This theory is simplest TQT in 3+1D. Here the B is two-form U1 gauge field. So here we carry two Lorentz indices. So here's 1, 2, 3, 4. So 4 forms. We use this 4 form anti-symmetric tensor to contract all the mu lambda room together. Then we end up with a scalar action scalar. So here's the BF theory, and based on this BF theory, we can compute this particle loop braiding, which is nothing but edge phase. You can regard this, for example, when n equals 2, you can regard this process as some process in superconductor. So you can have electron go around some pi flux. Within the ground state, we end up the phase -1. So here's so-called particle loop braiding. And in addition to particle loop braiding, we can also have some twisted version by add additional topological terms, the AA and A1, A2, DA2, or A2, A1, DA1, or A1, A2, DA3. And as long as you have 4-form wedge product, this is very simplest generalization of BF theory. For twisted BF theory, And also, we can also have some AAB term. Once we add an AAB term, we can have much more complicated braiding process, such as sweep and BR braiding, form braiding. So I have a lot of time. I don't have time to describe detail here. But if you are interested, you can read this whole paper, the original paper. So here, okay. So here, so then we still try to apply this Chern-Simons theory to describe the 3D phase, and there are still a chance, and the chance that we regard this ij instance as a coordinate along z direction, right? So now this a mu I x y t, this field becomes the a mu x y I t. So this instance I now becomes the coordinate the z direction. So now the simplest the simple example is this trivial starting was this one to log thing. So now although the formally we still have this action, this d3x, but now this ij we need to reinterpret this ij as the coordinate along z direction. So now it's intrinsically 3 plus 1d theory, right? 3 plus 1d theory. In fact, this line of thinking coming from this construction of the quasi 3D fractional quantum Hall effect many years ago, maybe in this famous paper by Michael Lehman and Fisher in this field, as far as I know. And recently, people reuse this line of thinking to study this so-called 3D Fracton topology. I need to explain what is a Fracton and what is a 3D Fracton topology. Okay.
So now that we have the DF theory as T to FT, why do you still want to apply Chern-Simons to P? And what is the original expectation?
You mean?
Yeah, now that we already have TFT theory,
yeah,
3D.
Yeah.
And why do you still want?
Yeah. I need to explain later. So basically, I want to use this Chern-Simons theory to describe some 3D topology called Fracton topology. For example, for this K-matrix, if we reinterpret ij as this coordinate along this z direction, the cycling direction, then you can find that the quasi-particle of each layer cannot commonly to each other. So in this way, we can say that this area now the quasi-particle have some restricted mobility. They can only move in some subspace. So this is our starting motivation to try to construct the 3D topology with quasi-particle that have some completely or partially restricted mobility. So this is our motivation to here. Okay, so let me show one slide to give a quick review about this so-called Fracton physics. So here are the two lines. The first line is we can regard this Fracton as topological partition. So-called in this so-called Fracton topology. Here's some typo here. So here Fracton in general sense can be regarded as quasi-particles that cannot freely move. They can only move only in some subdimensional space, subspace. So for example, here is the model. Here is so-called 3D model. We can have this Fracton labeled by this minus eigenvalue of this cube term, AC term. AC term is formed by 12 poly X here. So this quasi-particle cannot be moved freely. You don't have some fundamental deformable string operator to move this particle to another place. So here we say we call such particle such a topological quasi-particle as fractons. The second line is we can regard this fracton as some constituent particle in some many-body system that conserve high moments. So there are many properties here. I don't have time to describe the detail about this now. If you have some interest, you can read this paper. Okay, so let's go back to look at our idea to regard this K-matrix Chern-Simons theory as some 3D 3+1D TQFT. So here we consider some more general way this K-matrix rather than this K. This K is too simple, right? So here we consider this K-matrix. So here there's this A is 2×2 matrix, and B is also 2×2 matrix. So here this K is a translational environment along each diagonal line, right? So this K is nothing but a tridiagonal Toeplitz matrix here. So before we added B matrix, this A describes this ZM topological frequency layer, and then on top of that, we added B matrix. This B matrix describes the intercoupling without breaking translation symmetry along Z direction. And there is very important point that this B is local. So here we only need to add this local interaction between these layers. So we don't need to add this non-local topological coupling here. So we start with this K-matrix, try to understand the boundary effect. So naively, we have this two very different boundary, the so-called XY boundary and this Z boundary. And on this XY boundary, we expect that there is some chiral from liquid, which is very standard, right? So now our question is that are there any non-trivial phenomena on this Z boundary, upper boundary, and lower boundary? This is a new boundary, right? This is a new boundary and have not yet been studied before. Okay, so here before we talking about this context of Chern-Simons theory, once we have this K-matrix, we quickly remember that the existence of a Toeplitz matrix reminds us of this very famous topological insulator and topological superconductor.
Is any given?
Which
Not that different. But which is
you mean as part of
little
N? Here we study as N is given, and you can also N is odd. So here we I remember my example always N is given. I want to try to avoid formula example. So okay. So here yeah.
So is the boundary condition of C boundary unique?
Open. I use open boundary. Once you want to study whether or not the bulk is garbage, you can use this pure boundary condition by add some additional term here, this lower left and upper right. And here we only study as an open boundary because we want to try to understand what are this and non-trivial phenomena on the Z boundary. So we just use this very simple open boundary condition in this K-matrix. Okay. Now, the existence of this kind of vector reminds us this very famous TTI, TSI, TSC. This is very famous 10 years ago, more than 10 years ago. So very, very developed area in the field. Okay, so here we found that we have this. Once we have this K-matrix as Hamiltonian of this topological illustrator, the question we want to ask is: are there some non-trivial boundary remote or garbage state boundary that are protected by some symmetry? This is very famous story. So this temporal wave classification of the topological illustrator and topological superconductor this famous result. And now, because of this similarity of the mathematical structure, we want to ask: once we have this boundary remote on this K-matrix, are there some non-trivial results in my context, right? In my context, this is our motivation. This is our motivation. So basically, if K-matrix is a free-forming Hamiltonian matrix formally, but remember that now we have to enforce the condition that all entry of this K-matrix must be integer, because we need to guarantee this large gauge transformation. No, right? And this is only difference here. What happens if K-matrix have zero modes on the Z function? So
by having zero modes, you mean it has some eigenvalue being zero?
Yeah, right. On the boundary.
On the boundary, what does it mean to be on the boundary?
I mean that I can say on the boundary. I can say H say. Yeah. So our key finding, take-home message, is a so-called Toeplitz braiding. I create the name. You can just figure out the strange name. Yes. Okay. So the result is that once we have the boundary label of the K and some additional minor condition, this minor is non-integer upper right and those left elements of K, but because in some very rare case, there are some you must avoid the real case, because there's this braiding phase maybe 2 pi 2 pi 0, 2 pi 0. We must avoid that very real case. The main necessary condition is boundary remote of K. Then we combine these two conditions together, we have so-called Toeplitz braiding. So what is Toeplitz braiding? Then we define this braiding process as following. This braiding phase angle theta between this upper area and the lower area are always oscillating, not converge to 0 more 2 pi. Even though this the size is thermodynamically large. Here we must remember that the system size along x and y already at the thermodynamic limit, because we use Chern-Simons theory to describe each layer. So this xy direction already in the thermodynamic limit. But along this direction, we still starting because it's K-matrix. We start with finite dimensional K-matrix. So our starting point is finite dimensional along this direction. Okay, this pointer has no power. Okay.
What is this braiding?
Yeah. I have a teacher here. Once you braid this upper area, as long as the projection will lower area on the upper boundary are exactly inside this circle, then this upper area will pick up phase. Now, because then we can imagine that this braiding process happens in different universe, parallel universe. So it's very strange. It's very strange braiding process, and there is some connection, some talk, communication between two very far away parallel universe. So this is a very strange braiding process.
So it means that if two ends are getting braided on the upper boundary
and the lower.
and the lower.
Yeah. So you can basically you can fix one and braid another, as long as the lower area is projection exactly inside this circle for upper area, then you have this fix. And what I want to claim is that as long as the K-matrix has boundary symbol, and we as well as some additional minor condition, then we end up with the conclusion that this braiding phase angle always oscillating, not converge to 0 or 2 pi, even though the size along z direction is in thermodynamic large. Okay. This is a definition of Toeplitz braiding because we use this feature of properties of Toeplitz matrices.
There's one more question.
Yeah. Oh, yeah.
So what's the difference between Toeplitz braiding and the conventional braiding statistics?
I already explained that basically conventional braiding that two area in general must be in the same universe, same 2+1, same 2+1. For example, here is the area, here the area you braid one area along the other. We keep up the phase. But now these two areas are in different 2+1 space time. They are separated by a very large distance along the z direction, actual dimension. So this way we call it as Toeplitz braiding, the new kind of braiding. Okay. So here, just take a simple example, Su-Schrieffer-Heeger Hamiltonian. This is a very simple free-formula topological instrument in 1+1 D. It's very simple Hamiltonian. So here is forget about this K. You can write H here. You are comfortable, right? So here is a B. So here is a K is a symmetric Hamiltonian, real symmetric Hamiltonian. So Hamiltonian is convention. This so-called Hamiltonian is convention, and this Hamiltonian has two phases: trivial phase, non-trivial phase. In the non-trivial phase, we have this boundary involved, right? There's a topological incident protected by chiral symmetry. If I remember correctly, I don't know what is chiral symmetry. It's very complicated definition of chiral symmetry. So here is A and B, A and B. So A is A and B is A, right? So here we find that for this example is very simple, and we can analytically compute K inverse can be analytically computed based on this paper, and we can analytically compute K. It's very important results. And we found that if you want to have this non-trivial braiding between upper area and the lower area, at least we have non-zero lower left and upper right elements of this K inverse, right? Lower left, upper right K inverse. So here we find that when upper value n is larger than the L, then this space is trivial space. We know that. And we also find the theta upper this theta angle exponential data to 0, right? The exponential data. But if we choose the parameter region like m is this n is smaller than L, then this topological incident in 1D is topologically non-trivial as a boundary symbol. Then this lower left and upper right. Here, if we compute this braiding phase between upper area and lower area, we need to use this lower left elements for upper right elements because the symmetry we're just using the lower left is not. So we found that in this primary region, this theta before we mod 2 pi, this theta has permanent not, right? So then once you mod 2 pi, this theta actually is permanently oscillating in this first Brownian zone, right? In first Brownian zone, because theta is the definable 2 pi, right? Definable, right? So in this broad region, we in fact have some non-trivial Toeplitz braiding between upper area and lower area. But here we have some additional minor conditioning to avoid 2 pi or 2 pi phase, because 2 pi, 4 pi, 6 pi all are equal to 0. So we must avoid this minor cases, real cases. Okay, this is condition. So here we plot this numerical result, simply work that. We find once we have the trivial topological system, which means that we don't have boundary involved. For example, and when L is 2, here L is 1, we find that's theta. When we increase this system size, we find that's the theta roughly come to 0, right? So here, once we have non-trivial topological system, we have this oscillating structure for the system when you increase this system size. So here, no matter how large the system size, infinite system size, we still have non-zero theta. Maybe on the maybe when you have some spatial n, this theta accidentally is 0. That's fine, but once you increase a little bit, it will become non-zero, right? This is the feature of this non-trivial Toeplitz braiding between upper annual and lower annual, right?
For the upper annual, the L vector is 1, 0, 0, 0, and for the lower annual,
and basically you can try to use maybe 0, 1, 0, maybe 0, 1, 0, 0, and as long as you have some non-trivial and non-trivial Toeplitz between upper annual, you and lower annual, you can choose this vector properly because you have some complex unit cell with 2 layers, 3 layers, yes, you are correct. The way we can choose 1, 0, or 0, 1, 0, 0, 0, 1, 0, as long as this non-zero component near boundary, near boundary, that's fine. That's okay.
Sorry. Yeah, so do you have condition on the type of techniques? I mean, for example, for 2 elements in the same layer, if they have non-trivial braiding.
Yeah.
And does it mean that they have non-trivial braiding?
You're right. So here I just this is a statement of existence. As long as I have some non-trivial non-trivial Toeplitz braiding. One way to do that, you just pick up the so-called simplest area, like the 1/3 area, 1/3 area. That's because once you have non-trivial Toeplitz braiding between 1/3 area, and then you can say that the braiding between 2/3 area always here, right? So here you must try to find the solution. Okay, so now the direct question is that are there any symmetry requirements for this Toeplitz braiding? Because in topological incident and topological superconductor, for the temporal wave classification, we need this strong requirement of symmetry. So do we need some global symmetry to protect this phenomenon? The answer is no. Because this gating one of Chern-Simons theory automatically guarantees integer quantized symmetric n to k. So as long as 3D block is not closed, it's open here. So this coefficient, this k is already quantized. As long as this focus is gapped, right? So we don't need any additional global symmetry to protect this phenomenon. It's pure topological. We don't need additional chiral symmetry, whatever. Time also symmetry. We don't need any symmetry. Okay. If you insist on symmetry, we can see we have gauge symmetry to protect this thing, right? Although some people say that gauge symmetry is redundant, that's fine. so here we don't need some global symmetry over conventional definition to protect this thing. This is very important point.
It seems that you need to have translation solutions into.
Yeah, no, yeah, you are right. So this is very important point. Maybe next time I want to add some additional defect to detect this. I don't know. This is very important in future development. In fact, it's very important future to add some additional violation of this translation part. So I don't know. So here the second question is that why boundary mode leads to this Toeplitz breaking. So in other words, why the robust why the boundary mode of K-matrix leads to the robust non-vanishing lower left and upper right of K inverse. This is pure mathematical thing, mathematical problem. So in the present with this quasi-zero mode, because we start with finite finite sets, we don't have absolutely zero mode. It's only quasi-zero mode. This lambda 1, lambda 2 are two zero mode, which are quasi-zero mode. It's very small but finite because our dimension the size is finite. Our starting point is finite. So in the present this quasi-zero mode, this K inverse can be formally expressed in this way. The first two terms coming from this quasi-zero mode. This V1, V2 is bounding, anti-bounding wave function, bounding, anti-bounding wave function, and lambda 1, lambda 2 are corresponding quasi-zero mode, which is finite, but very small but finite. And once the system size becomes very large, we can have we can use this M matrix to give a very good approximation to this K inverse. We can forget about this certain second etc. We only preserve the first two terms, this K inverse. Then we can use this matrix to give a very good approximation to this K inverse, because in general case we don't have this analytical way to solve this K inverse, right? K inverse is very hard problem. But in some special case, for this, with K is SSH Hamiltonian, we can compute the K inverse. But in the general case, we don't have an analytical way to compute the inverse in K matrix. So here we have a way to approximate this K inverse by using this M matrix. We just preserve the first two terms that are contributed by this quasi-zero mode. We find that in this approximation, the lower left and upper right matrix elements successfully reproduce this exponentially enhanced lower left and upper right matrix elements tables. So here,
what's the definition for quasi-zero?
Quasi-zero is like here you have V1, V2. The corresponding wave functions are gradually localized on the boundary when you increase the system size, because in general the system size is finite. When you increase the n, then this V1, V2 will localized on the boundary. So the corresponding eigenvalue, we call it quasi-zero mode. Okay.
So the value of lambda 1, lambda 2 may not be very big.
It's finite,
Very small.
it's very small, but it's finite. When you have finite and finite n, but when you approach this n to infinite,
It really goes to zero.
yeah, zero mode. Yeah. Because we already said in the present. Oh, okay. Our starting point that assume that K has boundary zero mode. But when you do this ED calculation, you have finite size system. There is no exact zero mode here. So right. So but it's a quasi mode is very small but finite. Once you approach this thermodynamics, we have this very good extractive relation to this absolute zero.
What's the relation between being exponentially localized on the boundary for the wave function and being very close to zero for the lambda?
Oh, I think these two things happen simultaneously. I don't have very good understanding for this thing, but
I think this requires some assumptions of the K-matrix. For example, I add some identity to the K-matrix.
Yeah.
It doesn't change the profiles of the wave functions, but
Yeah.
the lambdas will change.
Yeah, but we may discuss later, but here what I want to say is that we have this translation invariant K-matrix. So this Toeplitz K-matrix, once you increase this system size, you must preserve this translation symmetry. So this identity may be avoided.
It is translation invariant that this identity is just a diagonal matrix with some, say, even entries.
Where in matrix? So
Yeah.
so here.
Yeah,
right?
it's just some diagonal matrix.
That was it.
Yeah. With the same entry, I believe. Yeah.
So here,
No, just a identity matrix.
identity matrix.
I'm just adding some identity matrix to the image.
Yeah. This identity matrix may be regarded as unset. I think unset computation or something like that. But yeah, my understanding is that once you add this identity matrix and study this topological invariant this candidates in the context of topological. Once this topological invariant non-zero, we can follow this result of the topological.
But the topological invariant of the topological bands is defined using the block-tridiagonal functions, not using the spectrum.
Yeah. Yes, you are right. So here is some orthogonal correspondence. Once you have non-trivial topological invariant, we claim that there's some unreasonable. This is the result.
But I think in general, there needs to be some additional conditions to relate a small lambda to localize V.
Sorry, may I some answers our question?
Yeah.
And if you add some Hamilton or some on-site potential to the specific model, you just shift the whole spectrum to constant, and it doesn't really change the eigen wave function.
Yeah.
And if you just apply the same transformation inverse of that whole matrix, I don't think it will affect much. Because you can always subscript the on-site potential, and it will not change the topology.
Maybe we need to redefine this zero and z. Is that right? Redefine the.
Yeah, we can shift the whole spectrum to up to a constant.
Yeah.
But the interesting point is the lambda at that time might not be really small. Then how do you know that one more lambda really dominates the inverse? That may not be clear.
Yeah.
That's suppose important point is belongs here.
And it's something we want to make this.
Yeah, I'm not sure here. Maybe we need to add some more condition, but I think
Usually when we see localized modes have zero energy, that's already assuming the block content has some kind of particle symmetry.
particle symmetry.
That's why the spectrum looks so symmetric. And if there are some modes localized, is localized in the middle. Otherwise, it can be shifted.
Yeah.
And in SSM model, the zero mode is protected by the arithmetic, and it just fills the sigma y components, and the identity matrix will not affect the logical aspects of this model.
Yeah, that's right. So the topological aspects is determined by the wave functions, not by the spectrum. But here, it seems we are making use of the smallest of lambda to approximate the entire inverse using the first two terms.
Yeah, here we just want to understand this asymptotical behavior of this matrix. Maybe we don't want to talk too much about this something. We just okay. We here want to analytical to understand this asymptotical behavior finite size. Just some way to do the calculation.
If I understand correctly, this unconventional Toeplitz braiding actually can be boiled down to the diverging boundary components of the inverse matrix.
Yeah.
And I suppose that we have so many ways to do that in a 1D lattice system.
Yeah.
Like a
Yes.
right.
Yes.
We can always do that.
Yeah. As long as you have this chemistry with non-zero boundary remote, we can use this this chemistry to realize this Toeplitz braiding. We just follow this matrix from free forming topology.
Yeah, I guess you are assuming that zero mode happens at a boundary. In general, the zero mode doesn't have to have a boundary.
So here we assume the boundary remote. Maybe you have both remote. Okay, you're right. So here we assume the bulk is gap. If we interpret this K as Hamiltonian, we have topological instrument.
And also the boundary mode may not, for the boundary mode not be zero. If I shift the entire K-matrix as my
You're right. Maybe we need to design this K-matrix very carefully. Here we really need this boundary mode. Maybe you have some very fine design for this K-matrix. That's fine. So here we don't talk about this how to design this K-matrix, but we are talking about this condition. We need this boundary mode. How to realize boundary mode? That is alternative discussion.
Okay, another question is, we focus on the first two terms, and there are another 2n minus 2 terms. When n is large, it's not clear to me that other terms are small.
Yeah. Okay. I'm physicist. Okay. I'm physicist. What I will allow to answer your question. we assume they're small, right? We assume they're small because our numerical results they are small, so they are small, right? That's right. So. We are not mathematicians, right? So we find okay that for boundary remote there are two types. There are two zero modes and one zero mode. We find that in type 1 there's TI, TSI, but type 2 they are not present TI, TSI, maybe are not physical in that context. That's fine. They are the mathematical result. So there's two boundary remote, one boundary remote. So in general, and here there are some numerical calculation of second and third, fourth example because the first example is affected on mode I already showed. So here's type 1, type 2, type 2. Here we find that this picture of the basic element plot of the K inverse. We find this all these examples are non-trivial, have this non-trivial Toeplitz braiding because there's a K inverse has non-trivial, non-zero lower left and upper right. Even the system size is bigger and bigger. So here we find that indeed this theta angle is oscillating when you increase the system size. This is numerical calculation, which is much more simple. So here this trivial one, the fifth example is trivial. Once you have this A, this B forming the K-matrix, we indeed have this distribution of the braiding phase angle are all localized along near this main diagonal. So this lower left and the upper right is flat. Right. So we don't have a signal. So here the phase angle roughly goes to zero. Roughly goes to zero. Exponential decay. And okay, because we can add additional symmetry charge here, so we can calculate the so-called charge population of anion with each layer. So we found this when you have non-trivial Toeplitz braiding, the charge population distribution of on the z direction are oscillating randomly oscillating, and when you consider open boundary condition, but when you consider PDC, pure boundary condition, it's flat, so flat. And the same as the second example, the third example also shows a similar phenomenon like this. This two examples also are the same. But when you choose the fifth example, which has trivial Toeplitz braiding, and both OBC and PBC show the same result. When you put the system with open boundary condition along this direction, we don't have this random distribution, which means that open boundary and the pure boundary have the same result, have the same for the distribution with charge parameterization. Here, so by definition, this charge parameterization is model one. We already model is number one, because one is non-fractionized charge carried by electron or some trivial particle. So here I will have one or two slides. Here is on paper on progress. We put this we first starting 3D theory, 3D topological order along the fourth dimension. Now we expect that in some way we have some Toeplitz braiding between particle and loop. We put the particle in one boundary and loop on another boundary. This boundary is 3+1 boundary. The bulk is 4+1. So now can we have some very strange particle loop braiding? Although when you braid the particle cannot see there is a loop. So this very strange particle loop braiding, this analog is very strange, highly analog. So because these particle loops are separated by this very large fork, 4-dimensional, 4+1 length fork. So can we have some similar story? Yes, this is very interesting that now if you use this BF theory, K-matrix BF theory, now this KIT are allowed to be asymmetric. Now the popular direction, non-Hermitian physics. now we can borrow this very beautiful knowledge from non-Hermitian physics to study this strongly correlated PRD results. so here we found that we can use Hamiltonian type or non-Hermitian aesthetic model to study this because it's non-progress. I just show some here result here. So instead of symbols, we don't need to compute symbols. Here we just do this 3D composition for this K-matrix. We find that once you have the boundary labeled for this single boundary decomposition, instead of ED diagonalization, we have this Toeplitz braiding. This Toeplitz is very strange between the particle loop, this particle on this 3+1D universe loop on another 3+1D boundary. So it's parallel universe, they can feel each other, but they cannot see each other, they can feel each other in this topological experiment. Okay, this is some numerical result. We found this, and this is because now K can be asymmetric. So this K inverse is also asymmetric. So as long as either lower left or upper right are non-zero, and they can support this Toeplitz braiding. As well as we add additional minor condition to avoid the 2π, the trivial 2π, 4π, the 2π mod 0, right? So we add additional minor condition. We find that there is non-trivial Toeplitz braiding. This Toeplitz braiding is particle loop braiding between particle loop from different universe. Okay, this is summary outlook. We define a new type of braiding, Toeplitz braiding as boundary phenomenon of Fracton topology order in 3D and 4D. We use the knowledge of free-forming topology illustrator and non-Hermitian physics to strongly correlate topological phases to reach this result, reach its conclusion. There may exist a very interesting boundary phenomenon in this new type of topology order. And for the future direction, maybe we can compute this entanglement scaling by track along with z direction to study this entanglement between the two subdimensions. And also we can construct lattice model inspired by Fracton composite formula. Fractal placement, we always add some energy penalty to enforce this flux particle bonding to reach this Chern-Simons surface. This is very scientific here to then we can use this use DMRG or quantum mechanical to study this lattice model. Okay, this is what has been in my this is my current research in my group in Yat-Sen University. We have very diverse interest, even ADSFT. Thanks for your attention. Welcome to visit us in Guangzhou, Canton.
And thank you, Professor, for the very nice talk. Any further questions?
I kind of want to know that in this phenomena, to what extent can we understand this phenomena as kind of 1D physics? Because but you also mentioned that the XY direction is extended.
Yeah.
And already at the thermodynamic.
Yeah.
If I imagine the system, the XY direction is kind of shrinking to a very small size, and somehow it's effectively a 1D understanding, like the quantum states, and the two ends are kind of entangled in some way. But here, is it possible to have such a picture?
Yeah, impossible, because we assume that there is already thermodynamic limit XY direction. We only borrow the mathematical result from topological and non-Hermitian physics. Actually, the physics between the two sides are completely different. We just borrow this mathematical result, the K-matrix, the Toeplitz matrix theory. I learned from Wikipedia.
From that perspective, that means when you increase the size along the z direction, do you have a good, at least in some sense, the thermodynamic limit?
Yeah.
Seems no, because your braiding theta braiding phase is not converged, right? Unless you pick up some.
You're right. Now the braiding phase is not converged to some fixed value. This is very feature of a non-liquid state. Now the fractional topology is non-liquid state. Non-liquid state. You don't have the very well-defined thermodynamics in a conventional calculation, because you see that gross density for this state matter are increased by increase this system size. Usually, like fractional hole or conventional like 3D topological model, the GST is finite. Is a fixed value, no matter how large the system size. The value is fixed, is a fixed value. But here in the GST, when you increase the layer, the GST must be increased in the simple case. Maybe in some other case, maybe oscillating, maybe small, larger. So in this we usually call it non-liquid. Maybe my definition is different from.
But you get the
scattering phase. Because the low energy fixed theory of this state is Chern-Simons theory. Chern-Simons is gap.
That means the correlation functions
short
two ends are
yes, short correlation. The conventional correlation is short range, but this braiding is entanglement theory, maybe. So this is the reason why I want to study the entanglement theory for this system. Maybe very interested in scaling. But I don't have a method to study from field theory way. I'm learning some paper by Edward Fracton. I still try to digest. That's very hard.
Maybe one comment related to your question. We can ask for the so-called upper and lower ends, what's the shape of their string operators? Normally, if we only consider one layer, the string operator will just be supported on this layer.
Yeah.
I think here the shape will be extended into the entire.
Yeah.
But if you excite two animals on the orbital, two animals on the upper top.
Yeah.
Do they still feel such weird? If you have to decided also decided together somehow the rainbow operator is kind of localized. Not sure.
You can, I've noticed started this when young, but as far as I know, this is abelian topology. That's very simple. Everything, every topological data is a simple structure that is sum, just add.
Okay.
But if you consider non-abelian, stacking non-abelian to non-abelian Chern-Simons theory to do that, that's a very complicated but very interesting direction, and beyond my capability.
I see. So regarding the Hamiltonian scaling, are you expecting something about this area?
Error law should be there because it gapped, but maybe some subleading. Subleading will be affected by the Toeplitz trading. This is my interest here. So I'm still working on, but it's very hard to compute the entropy from this usually perspective because you need to do this replica. So the entropy that's beyond my capability. So I asked my students to do that. So I try to learn. There's the original paper by Edward Fracton and maybe some other friends. So it's very hard to read.
Any other questions?
I have a question regarding the SSH and the vector model, and the only common point of these two models is actually the exponentially decaying localized space. And can we extend the picture of the inverse of the effective 1D component to a more generalized case, rather than to conceptually totally different models in 1D.
In 1D.
Yeah.
Here I will pick two examples, the SSH and
Yeah, I think
many other examples. I already actually I already use this mathematical structure, this Toeplitz braiding. You can do the job to connect this mathematical to Fermion here. Even you can use this 3D topology with the boundary Dirac home, that's fine. But as long as you open one boundary condition, that's Hamiltonian still that's Toeplitz braiding. No matter how many dimensions you have in the site of a topological illustrator, as long as you have one dimension or one boundary condition, open boundary condition, the other one is momentum space, then the Hamiltonian still Toeplitz braiding. Oh, here, so we have some general result here. The requirement to have this two boundaries, but here we still assume that A and B are simple 2x2 matrix. You can 3x3. That's a very complicated thing, but beyond that capability, because we just want to pick up some simple example demonstrate my physical results. That's fine because we are physicists. Maybe.
And if we add some more complicated boundary condition like the Mobius connection to the two boundaries, it's a modified this matrix.
Of course.
I suppose the inverse of that matrix will not differ to this scenery to a large extent.
Yeah, maybe only yeah, you're right. So I only have one paper to do that. Maybe we can do the next paper. And like this Mobius boundary condition for our simple people, we start with open boundary condition to have a paper get published, and we have confidence. This doable. This direction is doable. Next we can add some additional talk. Additional talk. Is appetite. Maybe it's appetite. We have some dessert. Maybe probably we have some dessert. Like the twist boundary condition and flux and confirm deconfirm phase transition will get field. As additional max return, blah blah. That's another bunch of very interesting projects. Yeah.
Thank you.
Well, yeah, we'll be here for a week. You can talk to him later.
I only have knowledge of 1D topological models and non-Hermitian physics, so I have no of good prior knowledge to this Chern-Simons theory.
Well, that's as of today. Maybe after 1 week, you will become an expert in K-matrix. K-matrix is very simple.
Yeah, very simple. Yeah. Yeah, I learned K-matrix when I was undergraduate. Very simple. Yeah, I graduated in 2007.
Any further questions? Okay, if not, let's thank the Dr.
Thank you.
Recording stopped.